Moving onward to Chapter 7. Chapter 7 deals with talking about gravity. Now we've been talking about mass. We've been talking about velocity. We've been talking about acceleration. So we've been dealing with all of those. Mass, velocity, acceleration. Well, what works best with all of those? The universe, the solar system. All right. We have planets, we have stars, we have very large objects with very high masses, and they're moving in motion, and also they're moving in kind of a circular motion. So they nicely tie together everything that we've talked about. So when we talk about 7.1, we're talking about planetary motion, which is kind of a field of physics that you could go into, astrophysicist, or you can be an astronomer, which is just a separate field of physics. So to review planetary motion, we're taking a time-traveling trip back to 8th grade, and we got to talk about a few astronomers. All right. First astronomer, well, remember, Copernicus. All right, 1543 is the first to say planets revolve around the sun. All right. Now, the technical term for that is when something revolves around the sun is heliocentric. Helio meaning sun, centric obviously meaning centered. The prior thought to that was geocentric, geo meaning earth, centric meaning center. So Copernicus in 1543 puts together the common model that we now have for our universe, or our solar system. Tycho Brahe verifies that we have a heliocentric universe using his instruments. Now remember, the telescope's not even invented yet, so this is by observations made with his own eye on a nightly basis in the nighttime sky. That's all he did, was observe things overnight. Then Kepler, who's an understudy for Brahe, takes this data that he's collected, and Kepler's kind of a mathematician, and he comes up with much, much, much more. And he starts analyzing and crunching the data. So left to right, we got Copernicus, Brahe, and Kepler, three good-looking dudes. So Kepler, being the mathematician, comes up with 3 laws that deal with planetary motion. The first law is that planets travel in ellipses with the sun at one focus point. Now, the question is, what is an ellipse? Well, an ellipse is really a circle that's kind of been squeezed down. And a circle, when you make a circle, it has one focus point. Right? And then everything is drawn around one focus point. An ellipse has 2 focus points, and everything is focused around those 2 points. Now the sun is one of those 2 points. If I go ahead and delete one of those, that is the sun. And you can see that the Earth or any other planet would be closer to the sun at one time in the year and farther away from at another time. So that's Kepler's first law. Planets travel in ellipses. Secondly, there's an imaginary line from the sun to a planet that sweeps out equal intervals. What the heck does that mean? Well, let's blow up this chart here and let's kind of explain that. What we have is essentially it covers the same amount of time in 1 month. It covers the same amount of space on that ellipse. So for example here we have A, B, C, D, E, F, G all the way around. Imagine that there's 12 months. A is January, B is February, C is March, and on and on and on and on. Now you can see that when we go from A to B, it travels quite a long distance along that ellipse. Now why does it do that? Well, it's closer to the sun, so the gravitational pull of the sun is going to be greater when it is closer, and it's going to whip it around real quick. But if you look at that, if we want to count the squares real quick, we can go 5, 15, 21, 26, 30. We're just going to, I'm an eyeball, it's close to 50. All right. Now, if we go all the way over to the other side here, and let's say this is August, when we go August to September, all right, because it's really far away from the sun, it's not moving as far, but it's still, since it's so far away, still covering the same amount. So if we wanted to count all the squares in here, it'd be around 50. So what that means is for equal amounts of time, so we say 30 days, it's still going to cover the same amount of space around the ellipse. That's essentially what Kepler is saying in his second law. All right. So Kepler's first law, transplanar ellipses. Second law is they sweep equal amounts of distance over the same amount of time. So that was Kepler's second law. His third law is math, and his third law relates the time it takes for a planet to travel or an object to travel and its radius. So the square ratio of the periods of any two planets is equal to the cube ratio of the average distance from the sun. What the heck does that mean? Essentially, it means this equation. TA over TB squared is equal to RA over RB cubed. T being the amount of time it takes to complete one revolution, a period, once all the way around, and R being the radius, the distance it is from the sun, or the distance it is from another sun or another planet, or whatever it's going around. So TA over TB is equal squared is equal to RA over RB cubed. So if we take a real life equation, all right, with real life numbers, Galileo found Io. Galileo, the famous scientist and astronomer. Galileo found Io, closest moon to Jupiter, has a period of 1.8 days and was 4.2 units from the center of Jupiter. Callisto, the fourth moon from Jupiter, has a period of 16.7 days. Predict Callisto's distance from Jupiter. So we are given three things. We are given the T of Io, how long it takes, the T of Callisto, how long it takes Callisto to go around, the radius of Io, and we need to solve for the radius of Callisto. So what we are going to do is we are going to use Kepler's third equation to help solve this. So we're going to go ahead and we're going to go RA over RB cubed is equal to TA over TB squared. Now, it does not matter which planet you choose or which object you choose as A or B, long as you say the same. So for all intensive purposes, I'm going to choose Io as A. So let's go ahead and plug in the radius for Io, which is 4.2, over the radius for Callisto, which we don't know, RB cubed, is equal to TA, the radius of Io, 1.8, over the period of Io is 1.8, over the period of Callisto, which is 16.7 squared. All right. Our next kind of piece of math is what we can do is we can go ahead and we can take 1.8. We can take 1.8 divided by 16.7 and square that. And when we do that, we are left with 4.2 over RB cubed is equal to 0.0116. Right. Now we have to get rid of our cube unit. Before we do anything else, we have to get rid of our cube unit. So you can take the cube root if your calculator has a cube root, or you can take it everything to the 1/3 power. Well, when we take it to the 1/3 power, that cancels out, and we're left with 4.2 over RB is equal to 0.226. All right. Now we should be able to go ahead and solve this problem. We go ahead and we arrange it, and we figure out after we arranged it algebraically that RB is equal to 18.6 units, but with sig figs, 19 units is the correct answer. So that is Kepler's third law in a nutshell. So these three laws, the first two are kind of words and ideas which were correct, and the third law is what we just solved here using the periods and radiuses of the planets. All right. When we continue to talk about planets, we have to talk about something that's kind of important: Newton's study of gravitational force. All right. Newton kind of observed gravity, and he said the force of attraction between two objects is equal to its mass. All right, we know that. Newton said that. We've studied that. Law of universal gravity. Objects are attracted to one another with a force proportional to the product of their masses and inversely proportional to the square distance between them. What that means is there's always a force between two objects. All right? The closer you are, the greater that force is going to be. Now, what you have to understand is that there is a force of gravity always between two objects. All right. If you're sitting at home right now, the table and the laptop or computer that you're watching there's gravitational force. They are being attracted to one another. The mouse and the keyboard are being attracted to one another. They don't move because their masses are so small, but they still have a gravitational force to one another. All right. So when we put this into an equation, our force between two objects that are attracted by gravity, our force is equal to capital G. And capital G and little g are different, and I'm going to explain capital G on the next slide. Force is equal to capital G times mass 1 times mass 2 divided by the radius of the object squared. All right. So if we take Kepler's third law and apply it to the universal gravity law, or universal gravitation law, we can combine them, and we get an equation for how long does it take an object to go around or orbit the sun or any other object. And we get t, which is period, is equal to 2 pi times the square root of r cubed divided by g, capital G, times ms. And ms is the mass of the satellite. So like if we were trying to figure out how long it takes for the moon to orbit, right, the moon would be our mass that we would use in that example. So that is ms is the mass of the satellite. Now, I said I'd talk about little g versus big G. All right. I have it highlighted in green because this is a huge distinguishing characteristic. For all intents and purposes so far this year, we've been using little g because we've been accelerating or talking about the acceleration of gravity due to Earth. When you are standing on Earth, all right, pretty much every object is going to be attracted to Earth at 9.8 meters per second because Earth is so large and every other object is so small, that is, we can calculate how fast Earth is going to accelerate objects. That's little g. Little g changes. If I go to Jupiter, the force of gravity on Jupiter is going to be different than it is on Earth. If I go to the moon, it's going to be different than it is on Earth. G is the universal constant for gravity. Right? G is the force of actual gravity between two objects. So between the keyboard and your mouse, the attraction of gravity is calculated using G. Between you and Earth, the force is calculated using G, capital G. Right. Between the water bottle and my desk, the force of gravity is calculated by G. Little g is the acceleration of gravity. Big G is studying the force of gravity. You can use both of them, but remember, big G, we're studying the force of gravity. It's a universal constant. That is how strong gravity is, the actual force. Right? The acceleration of gravity, little g, depends on the mass. So that is the difference. It was studied by Cavendish in 1798. Big G is a constant, 6.67 times 10 to the negative 11th. Right? Also, when calculating big G, right, when we figured out the force, right, when we figured out the mass of the force of gravity between everything, we were able to figure out the mass of Earth, and the mass of Earth is a constant, 5.98 times 10 to the 24th. All right. Adding a few thousand people a day is not going to change that by that much. So mass of the Earth, you have two constants here to kind of remember, and that will be given to you. Capital G and the mass of the Earth, and these constants will always be provided just like we've provided little g is 9.8. So that concludes section 7.1 on planetary motion. We're going to tie it in real nice with 7.2 here. So we have Kepler, Copernicus, Brahe. We study Kepler's laws. Kepler's laws really opened up our bag of tricks when it came to talking about gravity between two objects, not just the acceleration of gravity.